Okay, good morning. Welcome to the class of S6 minor. So, today we will be dealing with the module 2, which is MOSFET fundamentals and basic VLSI circuits. Okay. So, before we enter into what MOSFETs are, first let us go through a bit of basics, which you have studied in your first year. You might have studied bipolar junction transistor, which is known as BJT. So, you might have also studied diode. Okay, diodes are unipolar because their uh, current is due to only one type of carriers, that is the electrons. Okay. So in the case of bipolar junction transistors, uses both electrons and holes as the charge carriers. Okay. So what it does is it allows a small current injected at one of its terminals to control much larger current. That is, that small current injected at one of its terminals that is known as the base. Okay. uh, to control a much larger current flowing between the terminals. Okay, so the main terminals are between the source and the collector and the emitter. Okay, source and drain is for JFET and the MOSFET. So you have two types of PN junctions. First one is uh, between two semiconductors. Okay, so one is N type and P type. So you can see two uh, P regions are sandwiched. Sorry, N region is sandwiched between two P regions, which constitute a PNP type of bipolar junction transistor. A P region sandwiched between two N region constitutes a NPN transistor. Okay, and these are named as emitter, base, and collector. And the amount of doping, you know what doping is? Doping is adding impurity. We usually take pure form of a semiconductor, and what we do is, depending upon the type of impurities that we require, whether it is trivalent or pentavalent, we dope the semiconductors. Okay, so here the emitter region, the base region, and collector region for the respective operation of the BJT, they are doped very differently. Because emitter is a supplier of charge carriers, they are very heavily doped with respect to the collector region, which in turn is to just receive the current. Okay, so they are moderately doped, and base region, they should not supply any electrons, but only their uh, work is to inject the current. So the base region is made very small and very lightly doped. Okay. So this particular device is actually a current controlled device because, and hence it needs extra current biasing. So this is how the structure of a BJT is. Here you can see on the left hand side, you can see an NPN transistor where the collector and the emitter are both N regions and the base region is a P region. Okay. Below you can see the flow of current. Okay. So usually for the BJT to work, the emitter base junction is forward biased and the collector base junction is reverse biased for active region of operation. Okay. So you can see down for the collector, you see IE is the current, and for emitter, IE is the current, and collector IC is the current, IB is the current for base. Okay, so usually how the current flow is represented is, we have two types of representation. First is the conventional flow. So always when you talk about conventional flow, the flow of current will be from positive to negative. But when electrons are playing the major role, the currents will be constituted by the flow of electrons. So there will be another direction, which is shown, like say, if you are using majority carriers as electrons, the electrons will move in a different direction with respect to the conventional flow, because that is electrons are negative. So they will move to positive region. So in a NPN type, the majority charge carriers, because they are electrons, the conventional flow and the original flow of current will be in opposite direction. Okay. So you can see the symbol of a BJT here. First, to the left hand side bottom corner, you can see there is an arrowhead on the emitter showing that arrowhead outwards shows the conventional flow of current. positive, that is base region is positive, and to the emitter, the current is flowing. That is how the conventional flow is shown. So that is the arrowhead shown outwards. Okay. Then in the case of PNP region, PNP, you can see that the arrowhead is shown inside, showing the positive to negative current flow is like that. Okay. So these are the four regions in which you can operate. First one is a forward active or the main active region. Second is reverse active or just the opposite of the main active region. So it is known as inverse active or inverted. Third is the saturation region. And fourth is the cutoff region. Okay. So you can see in the first case, NPN, you can have emitter, base, and collector. So the voltages can be applied for a forward to reverse type of biasing. That is the active type of biasing. What you require is N should be connected to negative and P should be connected to positive for the emitter base region. So emitter voltage will be at a lower voltage than the base. Okay. But the base collector junction should be reverse bias. That means the base should be at a much lower potential than the collector. So that is why E less than B less than C. In the case of forward, because base region is P, the base region should have a greater voltage in both the junctions. That is emitter base junction and collector base junction, the base should have the highest voltage. That gives you the saturation mode. Reverse region, the base should have the lowest voltage, okay, with respect to emitter and collector. So that is why the emitter voltage is greater than base, less than collector. Then you have the reverse forward region, which is the reverse active region or the inverse active or simply the opposite of the forward region. Okay. There, the emitter voltage should be greater than base voltage. And the base, that is, the emitter should be reverse biased. Okay. And base should be forward biased. So the base voltage, which is P or positive region, should be given a much higher voltage than the collector. So that is why E greater than B greater than C. Okay. Why E greater than B? Because emitter base junction is reverse biased. So reverse bias means emitter is a negative region. So it should be at a much higher negative potential with respect to base. Okay. Similarly, the explanation is valid for PNP region. Okay. So BJT major applications, even now they are used in high-speed digital logic by CMOS, bipolar CMOS. That is a bit of modification of the BJT. Then it is used for amplifiers, temperature sensors, logarithm converters. Okay, these are the major applications of BJT.